Good morning, everybody, and welcome to day 131 of AP Physics. We're going to study moving fluids today, starting with continuity. What goes in must come out. In this pipe, fluid is flowing from left to right. You will notice that the left end of the pipe is narrower than the right end of the pipe. We're going to look at one small piece of that fluid as it moves through the pipe. So there's one small piece moving from left to right. It has its own volume and its own mass. The mass and volume won't change because the density of this fluid is constant. That's what an incompressible fluid means. So sometime later, as the fluid moves through the pipe is narrower. So that piece of fluid has the same volume and the same mass, but it's moving at a different speed in the narrower pipe. We'll call that second speed V2, the first speed V1. You'll notice that V2 is greater than V1 because the pipe is narrower there. The speed of a fluid is faster in a narrow pipe. Distance is speed times time. So we could say that the distance that piece of fluid moves initially is V1 times t. Later it moves a distance V2 times t in the same amount of time. So in a small time, the pieces move a distance of speed times time. The cross-sectional area of the fluid changes as it moves through the pipe. You'll notice that on the left side, the fluid has a wider cross-sectional area in its cylinder than the fluid on the right side of the pipe. Narrower pipe means a narrower cross-sectional area. But in both cases, we're describing the same mass of fluid. The mass of the first chunk is the same as its mass later on, just at a different time. Mass is density times volume. Volume for a cylinder is the area times the length of the cylinder, in this case, A times VT. You'll notice on the left side of the equation, it describes the left side of the image. The right side of the equation describes the right side of the image. Well, we can cancel out density and time from both sides, and we're left with A1V1 equals A2V2. That expresses conservation of mass. What goes in must come out. If the pipe's area decreases, the fluid flows faster. The units for area are square meters. The units for velocity are meters per second. So square meters times meters per second gives us a unit of cubic meters per second for the term AV. AV is called the flow rate of the fluid, the volume flow rate, cubic meters per second. So where in this pipe is the fluid fastest? Is it fastest at A? Is it fastest at B? Or is it fastest at C? Well, C has the narrowest pipe, so yeah, it's fastest at C. But what if we were to flip the pipe upside down? That changes nothing. The answer is still C. I think you get that. All right, enough of that. Here's water leaving a garden hose at a speed of 2 meters per second. If you were to cover up 90% of the opening with your thumb to make the opening 10% as large, or 1/10 as large, how would that change the speed of the water? Well, the initial speed is 2 meters per second, and the final cross-sectional area is 1/10 of the initial cross-sectional area. In this case, the speed is 20 meters per second, or 10 times as much. Another continuity question. Blood flows from your heart into your aorta at about 1/3 of a meter per second. But eventually it reaches your capillaries, where its speed is, significantly smaller, 0.34 millimeters per second. Can you find the effective cross-sectional area of your total capillary system? Notice I only gave you the radius of your aorta, not its diameter and not its area. Well, I hope you would want to start with AV equals AV. I went ahead and rearranged for the area of the capillaries. And remember, area is pi r squared. That's why I have 0.009 squared times pi for the area. Or, you have a lot of capillaries. You can do this lab at home if you want. Why is it that a stream of water coming out of a faucet is narrower at the bottom? Well, if A1 times V1 equals A2 times V2, and the water is definitely getting faster as it falls, then V2, or the velocity at the bottom, will be faster than V1, the velocity at the top. If V2 is greater, then A2 is smaller. And that's it. That's continuity. A1 V1 equals A2 V2. The biggest challenge with continuity is remembering the relationship between area and radius. Doubling the radius quadruples the area. Next up, we'll learn about Bernoulli's equation, which describes conservation of energy in an incompressible fluid. Continuity describes conservation of mass. Bernoulli describes conservation of energy. In order to derive Bernoulli's equation, we consider a section of fluid as it moves through a pipe. Here's a section of fluid, and here it is sometimes later. As that section flows, it might travel at different speeds, it might move to a different height, or it might be at different pressures. The pressure, the motion, and the height, they're all related through the conservation of energy. We have to remember that work is the product of a force and the distance over which that force acts. Kinetic energy is the energy of motion. That's 1/2 mv squared. And potential energy is the energy that fluid gains in the gravitational field and its interaction with Earth. The higher up the fluid is, the more potential energy there is in the fluid-Earth system. The law of conservation of energy says that the sum of all the types of energy in the system is always the same. So for a volume of fluid, that's the work done plus the kinetic energy plus the potential energy. We should always get the same number for that. So if conservation of energy is correct, spoiler alert, it is, the initial energy per unit volume equals the final energy per unit volume. Or the work done on a volume plus its changes in kinetic energy, its changes in potential energy, they tell us that the total energy is always the same. So there's a before and there's an after, separated by that equal sign. The total energy before a change equals the total energy after a change. Then some algebra happens. I don't feel like doing it for you. If we were in class, I would feel like doing it for you. The end result is that the initial pressure plus 1/2 rho v initial squared plus 1/2 rho g y squared, that's height above some arbitrary zero, not to be confused with pressure, which is rho g depth. This is rho g height. That's constant. That's the same in the initial state as it is in the final state. So if you were to want to write down Bernoulli's equation, which would be a great idea, you should write this. Pressure plus 1/2 rho v squared plus rho g y is constant. When College Board asks a question about Bernoulli's relationship, they tuck in a secret hidden question about continuity, often not giving you enough information to get the second velocity unless you apply the ideas of continuity. They will often give you an initial velocity, 2 radii of the pipes, and not give you the final velocity. So typically your first job is to find the second velocity Here's a sample question. I'm going to talk you through it, make sure that you can just follow along with the algebra here. Water is pumped at 0.5 meter per second through a 4 centimeter diameter pipe in a basement under 3 atmospheres of pressure. Yes, those are the circulator pumps that were in my basement. What is the flow speed and the pressure in a 2.6 centimeter diameter pipe, 5 meters above? So here's the question. We have pressure and velocity in a basement. And we have the height above the basement at which we want to know the other pressure. But we don't know the flow speed. So the first challenge is to find the flow speed using ideas of continuity. A1V1 equals A2V2. V2 is V1A1 over A2. We have everything that we need in order to find that. So we can find that the second velocity, the velocity upstairs, is 1.2 meters per second. Writing out Bernoulli's equation feels tedious and time-consuming. There are a lot of numbers to chase around, like the density of water, v squared, small areas, small radii being squared. Be careful. Write out your steps. It ends up being pretty easy to solve, but annoying to keep track of. So we do a little algebra, plug in the numbers, and find the pressure upstairs. If you want, you can practice it. You should be good at doing a question like this. But conceptually, here's the message. Here's a pipe. Here's fluid flowing through the pipe. Where there's high area, there's low velocity. Where there's a small area, there's high velocity at that pinch point, at that narrow part of the pipe. The water's speed is faster. So we write out Bernoulli's equation. P plus 1/2 rho v squared plus rho gy equals P plus 1/2 rho v squared plus rho gy. In this example, the y's are the same. If y1 equals y2, well, then we can cancel them out from both sides. In this example, v1, that's the velocity on the left, is less than v2, the velocity in the middle. If v1 is less than v2, then p1 is greater than p2. Where there is high velocity fluid, there is low pressure fluid. And we call that the Venturi effect. The Venturi effect says that if fluid is moving really fast, its pressure is lower. I can't show you this right now because I am not going to take a video of myself right now. If you take 2 pieces of paper and hold them dangling in front of you and blow down through both pieces of paper, through the middle of those pieces of paper, the 2 pieces of paper, well, I'll let you try it. Now, the Venturi effect, typing this slide, made me realize physics is full of great band names. You can almost hear which bands would play which style of music. Like, I might not go to an Unstable Equilibrium concert, but I would probably see a show by the Lorentz transformation. Anyhow, you can put your pencil down. You don't need to write this part. Here's one use of Bernoulli's principle and Venturi's idea that pressure is lower where the speed is faster. If we need to compare the speed of fluid as it flows through a pipe of different diameters, this is how we do it. If you are modeling the speed of air as it flows over an aircraft's wing, it's done with a Venturi meter. If you're checking the speed of liquid in a pipe, it's done with a Venturi meter. Attaching a narrow cylinder to that pipe and measuring the speed difference by comparing the pressure difference, and measuring the pressure difference by comparing a height difference. And that's pretty cool. We apply Bernoulli's principle, rearrange some stuff, the pressures are different, and then by the height difference, we can tell the velocity difference. That's pretty cool. You've probably heard about airplanes and lift. As air flows over the wing of a plane, there's faster speed air, lower pressure air on top, higher pressure air on the bottom, and you've probably seen it explained something like that. Higher pressure means more collisions per second, more force against the bottom of the wing. And that's kind of right. Except, of course, that it forgets about Newton's third law. When an airplane flies, the airplane pushes down on the air. The air pushes up on the airplane. If this definition of aerodynamic lift was completely correct, then airplanes wouldn't be able to fly upside down. And yet, I love this photo. You all remember Newton's third law, I hope. Downwash, that downward force that the airplane applies to the air. It swooshes the clouds behind the airplane. Imagine how much force it takes to lift an airplane. That's how hard the airplane is pushing down on the air. Here's how to throw a curveball. Because this is a top view of a baseball moving through the air. So we are looking down at the ground as the baseball moves. Because of air's viscosity, that means air is a little bit sticky. A spinning baseball will be surrounded by a thin layer of air that spins with it. So there's the air spinning with the baseball. As the baseball moves through the air, it is dragging this sticky air with it. Of course, the baseball will be flying into a strong wind. With respect to the ball's frame of reference, it's flying into a strong wind. There's the strong wind right now. I wasn't able to draw the vectors with relative length, meaning relative velocity, so I went with relative thickness, meaning relative velocity. The velocity of the air as it spins with the baseball is lower than the velocity of the air into which the baseball is being thrown. The vector sum of those velocities on either side of the ball will be slightly greater or slightly less than the wind speed, so let's add those vectors up. The faster air exerts less pressure on the ball, so the ball will travel to the side with faster air. All right, that's it. You know about continuity, you know about Bernoulli. Congratulations, everybody, and happy Monday.